My name is David Cochard. I'm a student at UTC, a French engineering school. Welcome to my presentation on the main project I completed in spring 2008 during a research semester at the Chiba Institute of Technology in Japan. Roughly speaking, my project was about merging several virtual reality technologies within a single application. I worked with augmented reality, haptics, and a physics engine. So what am I going to talk about in this video? First, I will present the different technologies I used, then the initial objectives of my project, and finally the results I got. Please note that this video does not contain much technical explanation. Its goal is to concisely present my project. I will provide you with the address of my personal website at the very end if you'd like to get more information. Now, let's begin with a brief description of the different technologies involved in this project. Augmented reality is achieved using live video from any digital camera. The live feed is processed and augmented by the addition of computer-generated graphics. This is the augmented video stream. The position and orientation of the coded target are used to calculate and realistically render a 3D model, a cone in this example, within the video stream. This technology can also be used for independently tracking several coded targets, each of them associated to a unique pattern and a unique 3D model. Haptic technology enables the user to interact with a virtual environment via the sense of touch. The system gives feedback to the user by providing forces, vibrations, or motions. This is one of the haptic devices I used during my project. I can really feel the 3D sphere, and the device doesn't let me move through it. It's pretty tough to illustrate that feeling in a video, but I do my best. Here, the blue cone represents the tip of the stylus I'm holding in my hand. One major challenge is to compute and schedule the forces sent to the haptic arm that give realistic feedback. A wide range of tactile sensations can be simulated, for example the roughness of a surface, the viscosity, inertia of an object, and so on. A physics engine is a computer program that simulates Newtonian physics using variables such as mass, velocity, friction, and so on. It can simulate and predict effects under different conditions that approximate what would happen in real-world scenarios. You can see in these example programs that the rigid bodies, like 3D dominoes, realistically collide with each other. They are affected by the simulated gravity as if they were existing in the real world. Now let's take a closer look at the objectives of this project. As mentioned before, augmented reality and haptics are two distinct technologies. The first aims to overlay 3D models onto a real-time video stream, whereas the second one enables the user to interact with a virtual environment via the sense of touch. The initial goal of my project was to merge these two technologies by creating a solution in which the user could haptically feel augmented objects. The latter objective has been achieved earlier than expected. So now what? I pack my stuff and fly back home? Of course not! My supervisor during this internship, Professor Nakamura, and I looked for different ways to enhance immersion and interaction. This video will present the most important results I got. We will be speaking about shadows, reflections, and other things that I really cannot explain with pieces of paper. My first significant result allows the user to haptically feel primitive augmented objects such as cones or cubes. The blue cone moving around the shape is called the proxy. It represents the haptic arm stylus and effector in the virtual environment. The interaction here is still unidirectional. Moving the marker towards the proxy causes forces to be sent into the device, hence the latter moves by itself and the user can feel the object. Conversely, there is still no way to move the shape out of its original location on the coded target. This one-way interaction is particularly obvious in the following multi-target configuration. I cannot move the cube which is static on its marker. However, we can see that the haptic arm moves when I push the marker towards the proxy. Now let's try to render nicer objects, more appealing than cones and cubes. Complex 3D models are usually created using applications like 3D Studio Max, which is currently on the screen. I implemented a module to my solution in order to easily import 3D Studio Max objects into an augmented environment without any prior conversion. Then we can see, feel, and animate any 3D model. Naturally, the next step in improving interaction was to move objects using the haptic device. There are two buttons on the stylus. I used them as selection and motion tools. The objects can be translated, rotated, or both at the same time, with the current mode being displayed at the top left corner of the screen. The workspace is controlled by turning and moving the marker around in one hand. In the meantime, the second hand can move models using the haptic device. Moving an object in a common 3D environment using a keyboard mouse usually requires at least two steps: moving the workspace and then moving the shape. This kind of interaction is greatly optimized here thanks to a natural 3D mapping between the virtual and the real environments and the ability to simultaneously manipulate workspace and objects. The first button is used to select or deselect a particular object in contact with a proxy, or all of the objects if there is no contact. Likewise, the second button is used to move the shape in contact or to change the current motion mode. Let's leave the field of haptics for a moment to tackle some existing problems with augmented reality. Since augmented objects lack credibility, I tried to come up with solutions to add realism to the effects. After the detection of the coded target, the generated graphics are simply overlaid on the original video stream. There is no further consideration of the real environment apart from the marker itself. A problem quickly appears, like in this example, when real objects are located in front of the augmented one. I worked on several methods to detect and then consider the real object so I could render the augmented model coherently. Then the user has a better and more accurate perception of the augmented environment, which is essential for industrial or medical applications using augmented reality technologies. Here is a real object and a similar augmented one placed next to each other. Anyone can quickly tell which one is real and which one is not, mainly because the augmented version is lacking shadows. Here's the result of adding shadows. Isn't that better? I enhanced my program to render object shadows in real time and lighten their textures. I used the haptic device to move the virtual light, which is represented by the blue cone. We can see that the shadow stretches and shrinks as the light turns around primitive objects, as well as models from 3D Studio Max. Another unavoidable natural effect from the real world is reflections from mirrors. In this demonstration, I use two mirrors which are tracked separately by coded targets. Note that the sphere is not located on the marker, but it has been offset so the marker doesn't occlude the mirror. The reflection is rendered in real time, moving the target as well as the mirror. Mirrors are essential tools in many fields where augmented reality is getting increasingly popular. For example, the use of this technology in surgery. Using an additional marker, a second mirror can be introduced in the environment. Of course, the latter will also reflect the augmented objects. There are other less intrusive methods that could be used to track mirrors in the environment, specifically pattern recognition on mirrors with predefined shapes. Let's place one of the mirrors perpendicularly to the table and see how the reflection reacts. That's pretty good, but since the shape is symmetrical, it's hard to tell if it's reflected properly. Here we are. Now, it's very easy to differentiate the faces of a die, and thus we can check the accuracy of the reflections. The mirror at the bottom reflects 6 dots, which makes perfect sense because the face with 1 dot is at the top. Rotating the die shows us that the reflection at the back is also correct. Finally, for the cherry on top, I added a physics engine acting on augmented objects in my system. This enables us to properly consider the forces applied by the user through the haptic device. In this first configuration, when I started the physics engine, it makes the objects fall down because of the gravity. I used a different kind of haptic arm for this part of the project, which offers greater possibilities regarding the size of the workspace, intensity of the forces, and so forth. The user can interact with any object producing realistic physical reactions according to the object's mechanical properties. Shapes can be smoothly and roughly pushed away, bounced on the desk, thrown against other objects, and so on. This last example combines the physics engine with one of the previous results we've seen by rendering shadows, which will be updated as the pyramid falls down. The virtual light is located around here.